Welcome Math 252. We're looking at problem 20 from section 6.3 of the Hughes-Hallett text. In this problem we're told that we've got a car going 80 feet per second, which is about 55 miles an hour, and it brakes to a stop in 5 seconds. We're supposed to assume that the deceleration of this vehicle is a constant number. So the brakes keep working just as well for the entire 5 seconds. We're supposed to graph the velocity function against time for those 5 seconds it takes for the car to come to a stop. We're supposed to represent as an area on the graph the total distance traveled between the times we hit the brakes until the car comes to a stop. And we're supposed to find the area that we've just found on the graph, and that's going to give us the distance traveled. Finally, we're supposed to do the same thing using anti-differentiation. So let's take a look at this. First, a couple of basic facts, and then we'll draw our picture. We've been told that the acceleration, or if you like the deceleration, same thing, is a constant number. So that says the velocity function must be a straight line. If the derivative of a function is a constant, then the function itself must be a line, and the derivative of the velocity function is the acceleration. So velocity is a line. Now, we know when time is equal to 0, so when we're looking at the intercept on the vertical axis, we're moving at 80 feet per second. So that gives us the intercept on the velocity axis. And we know that at 5 seconds, we've got our velocity down to 0, so we know that the intercept on the horizontal axis is sitting at 5 seconds. And that's all we need to draw a line. We've got 2 points on the line, so we draw the line. You can see the velocity axis is up and down, the time axis is horizontal. We've got an intercept of 80 feet per second on the vertical axis, and an intercept of 5 seconds on the horizontal axis, and I've drawn a line between them. The shaded area that you see on that graph is exactly the distance traveled, and so we calculate that distance, or that area, which is going to be a distance. We take half of the height, which is 80 feet per second, times the base, which is 5 seconds, and that gets us exactly 200 feet. So we've solved the problem graphically. We've done the first 3 parts of the problem. Now let's look at the last part where they ask us to do anti-differentiation. So we're basically solving a differential equation. We know that the car manages to lose 80 feet per second in 5 seconds. In those 5 seconds, it goes from 80 feet per second to 0 feet per second. And we know it's losing constant velocity at the same constant rate, so that rate's got to be 16 feet per second, since in 16 times 5 is 80, and it's got to lose those 80 feet per second in 5 seconds. So that tells us that if we write s of t for the position function, and I'm going to count s at 0 when we first start hitting the brakes, that's going to be the 0 position of my position function. So I'm going to start measuring distance from where I first put my foot on the brakes. Or to say it another way, I'm saying s of 0 is 0. So if I say that s of t is the position function, we just said that its second derivative, which is acceleration, is negative 16. Why does it have to be negative 16? Because we know we're losing velocity. In other words, the acceleration is acting to slow the car down, not speed it up. Okay, so once we know that the second derivative is negative 16, we integrate that to get the first derivative, s prime of t, which has got to be negative 16 times t plus a constant. But we know that constant has to be 80, the initial velocity, because s prime at t, or at 0, has to be 80. S prime at t is the velocity function we just graphed. So there's the line we just drew a picture of. And now we can integrate again to get the position function. We have s of t is negative 8t squared plus 80t. Again, we might think we have a constant integration, but that constant integration is going to be s of 0, the initial position, and I just said we were going to make that 0. We were going to start measuring distance from where the car was right as we first touched the brakes. Well, now we know the position of this car at all times, as long as this acceleration is being applied to it. And in particular, we can find out where the car is at time t equal 5 seconds. So we do that. We put in 5 for t, and you get negative 8 times 25 plus 400, which is also 200 feet, which answers the last part of the problem.